This conference will now be recorded.
Hello everyone. Today the topics that we are going to discuss: Charles' law, temperature-volume relationship. So in previous class we have started with the law, Boyle's law, which is basically relationship between P and V, pressure and volume. Now it is relationship between T and V, temperature and volume. So this is Charles' law, and then there will be graphical representation for this law, and after that Gay-Lussac's law, Avogadro's law, and if time permits, ideal gas equation. Fine. So PV relationship we have seen provided temperature is constant in that law. But now when it is Charles' law, as it is relationship between temperature and volume, so obviously we have to keep pressure constant. So as you can understand from this picture, when temperature is low, volume is low. Fine. And when temperature is high, volume is also increasing. So Charles and Gay-Lussac found that for a mixed mass of a gas, fixed mass of a gas, that means number of moles will be fixed. So in the previous law also we have seen, in case of Boyle's law, which is relationship between P and V, then also we have seen that we have kept T constant and also the mass constant, or you can say number of moles constant. So when these two are constant, then only you can establish relationship between P and V. And now we have T and V, so pressure will be fixed as well as mass, or you can say number of moles will be fixed. Then only we can compare. So they found that for a fixed mass of a gas at constant pressure, volume of a gas increases on increasing temperature and decreases on cooling, which you can understand from this picture. So it means that these two are directly related to each other, directly proportional to each other. Fine. But there are some more observations that we have to see. It was found by Charles that for each degree rise in temperature, there is a certain quantity by which the volume of the gas is increasing. And this quantity is 1 by 273.15 of the original volume. Original volume at 0 degrees centigrade. So suppose original volume at 0 degrees centigrade is V0. So now obviously with each degree rise in temperature there will be increase in volume, but how much? It will be increased by 1 by 273.15 fraction of V0. That means now original volume will be there and there will be some extra V0 divided by 273.15, and this amount will increase with 1 degree rise in temperature. So now we can establish this relationship provided that the volume of the gas at 0 degree centigrade and any temperature, suppose small t, which is mentioned here, T degree centigrade, it is V0 and Vt. So V0 is at 0 degree centigrade temperature, that is the corresponding volume, and Vt is the volume at any temperature, small t degree centigrade. It may be any temperature. So if this is the case, then what we can write? Now we can have this type of relationship. So when it is only 1 degree rise, suppose 1 degree rise. So previously it was 0 degree, that is V0 initial. So suppose it is at 0 degree centigrade and you are having the corresponding volume V0. And now you are increasing the temperature from 0 to 1 degree centigrade. So this will be the new volume. But suppose if we want to generalize, so now I will say, instead of 1, now I will say any temperature T. It may be any value. Okay. So in that case, obviously, now with this quantity, there will be this temperature T. So when it is V0 divided by 273.15 into 1, but now in place of 1, we are changing it to any temperature T. So that is why now the new relationship, that is the volume at temperature, any temperature, small t degree centigrade, the volume Vt, you can express it as if it is equal to V0 plus, basically if I write it like this, it is V0 plus V0 into T divided by 273.15. 15, 15, or you can simply write 273 for make it if you want to simplify. But V naught you can take common, so that is why inside bracket we have V naught into 1 plus T divided by 273.15. Now in Boyle's law we have seen graphical representation, that is pressure versus volume. In this case also, from this equation that we have written here, we can match it, that is you can correlate it with this type of equation, y equal to mx plus c, where c is intercept, m is slope, this will be the x-axis, whatever quantity we take, and there will be another axis which is y. So here what we will do for graphical representation, so these two equations, how we can correlate it. So y equal to ms plus c, and now I will write it as vt equal to v naught plus v naught 273.15 multiplied by t. Now I will write it here, that is y equal to mx plus c, and I will try to correlate it. So here Vt, you can compare it with y. This will be the intercept V naught by 273.15. This will be slope. Obviously, this is positive slope, and temperature will be in x-axis. So if we draw this graph, obviously the nature of the graph, it will be like this. Suppose you have taken volume in y and temperature in x, and there is intercept. So it will start something from here, and as it is positive slope, it will be like this. Suppose if it is negative slope, the nature of the graph should be like this, but that is not our case. In this case, slope is positive, so that is why the nature of the graph that will be like this. So this point where this is cutting here, that is intercept, this corresponding value, this amount of volume is basically V naught, that is the intercept. So now we will see the graphical representation. So if we here we have taken V in y and temperature in x. Now temperature, two scales you are seeing. First I will suggest just focus on the degree centigrade with which we are more habituated. So here we have 0 degree centigrade at the middle, and 100, 200 in this, it is increasing in the right hand side, and in the left hand side we have negative axis also, a negative x axis, and this side it is negative y axis. This is negative x. So it is 0, then 100 degrees and minus 100 degree, minus 200 degree. Fine. Now up to this point, I have already shown you the graph in the previous slide. But suppose if you are extrapolating this line in such a way so that it cut the x-axis. Now when it is cutting x-axis somewhere here, obviously at this point the volume is also 0, isn't it? Volume is also 0 because it has already touched this point. So at this point basically T is 0, V is also 0. But as that is this side we have positive V, then this is 0, this side we have negative volume. But at this point obviously volume is 0. So when you are extrapolating the straight line beyond the experimental measurement, suppose this is the point where experimental measurement, but suppose if we are extrapolating it, it is cutting the x-axis in the negative side obviously at this value, minus 273.15 degrees centigrade, sorry. And at this point obviously the volume of the gas is 0, which is clear from this picture. So here you can see this value, it is something in between minus 300 and minus 200 after 250, after minus 250. So it is minus 273.1. So this is the observation if we are extrapolating this line. Now what is the significance of it? Now another scale of temperature will come into picture. So where it is cutting this negative x-axis, this corresponding temperature, which is in degree centigrade unit, it is minus 273.15. But if we have another unit where we will consider this value as 0. That unit is basically Kelvin scale. So this is 0 Kelvin. So that is the reason when it is minus 273 degrees centigrade, that is actually equal to 0 Kelvin. Okay. Similarly, if I say that 0 degrees centigrade, which is obviously greater than minus 273, now the corresponding value in Kelvin scale, that will be, that is, you just have to increase this amount 273. Okay, so in this way, if I am saying suppose 25 degrees centigrade, so just add 273. So when you add 273, it will be 298 Kelvin. So when it is 0, it is 273 Kelvin, like this. Fine. So now we are getting another scale. So beyond this temperature, the gas will have negative volume. Now this is not physically possible. How it is possible that gas will have negative volume? Now beyond this temperature means this point. So at this point volume is 0, but suppose when you are further increasing, now you are reaching the negative zone of V, but that is not possible. It is physically impossible. So this is a maximum point you can reach, further you cannot move, right? So that is the reason this temperature value minus 273, it is considered as absolute 0 in the Kelvin scale. So as we cannot move further because volume will be negative, which is not possible, because of this reason the temperature was defined as absolute 0 in the Kelvin scale. And he proposed a new temperature scale with absolute 0 as starting point. So this is another scale of temperature, where starting point is 0 Kelvin, and in that is if you compare with degree centigrade, it is minus 273 degree. So whenever you get any value in degree centigrade, if you want to convert to Kelvin, you just have to add 273. And if you do the reverse, that is if you have any value in Kelvin, you are trying to convert it to degree centigrade, now you have to subtract it, right? So this is the two scales, how you can compare 0 degree centigrade when it is Celsius scale, that is equivalent to 273.15. Though we do not consider this 15, we simply say 273 Kelvin, which is absolute scale. So this is the minimum temperature possible. Further, if you move, suppose if you are saying minus Kelvin, why it is not possible? Because when it is minus Kelvin, volume will also be 0. So that is why it is not possible. So here we have this Vt equal to V naught plus, which we have already seen, and if we take this V naught common, we will have this type of equation. Now, if we write this quantity in the form of capital T subscript small t, because here this T is we are using as subscript, and if we consider this value as capital T naught in this equation, then the equation will change like this. See, Vt as it is left hand side, V naught as it is, but now you can also write it V naught 273.15 plus T divided by 273.1. That means now this value you are putting Tt and this value you are putting T naught. So obviously you will get this equation. If you simply rearrange, it will be Vt by V naught and T by T naught, which means what? It means if you consider it for any initial and final, suppose initial is 1 and final stage is 2, or you can write Vi, Vf. I means initial, F means final. So whatever you do, whatever subscript you use for two separate conditions, the relationship it will be like this, whether it is Vt or 0, 2 or 1, or I or F, any superscript you use. But the important point is now you can write this equation. So as V by T is constant, which though in the law we have already said it. Remember in the first slide of Charles' law what we have said, that V is directly proportional to T. That we already, that is a law. But here we can prove also mathematically like this. So if V by T, this ratio is constant. That means V is proportional to T, because when you remove this proportionality sign, then you get some constant into T, and you can write V by T is equal to constant. Okay. So again, we can say this Charles law, which states that pressure remaining constant, the volume of fixed mass of a gas is directly proportional to its absolute temperature. So previous law that we have said, remember it is in different way we have said. We have said that for a fixed, just first line, read the first line, fixed mass of gas constant temperature, volume of gas increase on increasing temperature and decrease on cooling. But another way also we can say Charles law, which is how it is related to absolute scale. So pressure, mass, these two fixed. Under that condition, volume of a gas, that will be directly proportional to absolute temperature. And absolute temperature, you can consider this capital T. Okay. Some more graphical representation we'll see. So when it is V versus T, suppose when T is in degree centigrade, now this is 0 degree, and if you are extrapolating the line, it is cutting at minus 273. But suppose, as we know that 0 Kelvin is equal to 273 degrees centigrade. That means if we start the scale here, considering at 0, the nature of the graph, it will be like this. Now temperature, it is in Kelvin scale, not degree centigrade. So in this way, it can change also. Okay. So now 0 is our starting point. So we have just shifted this line. That is the only difference. Now a new thing you will see. Remember in Boyle's law, where P is proportional to V, that is the relationship, or you can say that P by V is equal to constant. Sorry, it is inverse. Sorry, it is inverse relationship, not directly proportional. But I am trying to say, when we have considered in Boyle's law that P V, that is the relationship between P and V, then keeping temperature constant, and you can take several temperature value, suppose T1, T2, T3, you can draw the P versus V curve. But in this case, as the relationship is between V and T, so obviously at different pressure P1, P2, P3, we can draw 3 to 4 graphs, suppose P1, P2 up to P4. Just we have done the same thing for Boyle's law also. But in that case, as it is PV relationship, at different temperature, we have drawn the line T1, T2, T3, 4 like this. But now it is P1, P2, P3 because pressure is fixed. So at different value of pressure, where P1 is greater than P2 and P2 is greater than P3, the nature of the graph, it will be like this. So in this case, this is 0 degree centigrade. So in the x-axis, temperature is taken is degree centigrade unit, not absolute scale. So if you just focus on the right hand side of 0 degree centigrade, so this is the intercept for when it is pressure P3. This is the intercept when the pressure is fixed at P2. This is the intercept for the pressure when it is fixed at P1. And if you are drawing that, if you are extrapolating all these lines, it will cut at this temperature. So all are cutting at same temperature. Okay. So that is true. And just for the scale, you can understand easily here, and minus 100 is mentioned. See, if it is minus 100, then at the same distance, if you move, it will be plus 100 percent. So this is the relationship. Vt is equal to V naught. Then, or you can write it like this. Okay. And if you finally write Vt is equal to, so we have already reached how, that is from this equation to this equation. In the previous slide, we have already seen how to draw. So when at different temperature we have drawn the PV curve in Boyle's law, we have called all these lines isotherm. But when it is pressure fixed and at different pressure you are drawing all these lines, now each line of this V versus T graph will be called isobar. Remember the term isobar. Isotherm means temperature fixed, and these are isobar, P3, P2, P1 at different pressure. And you can also see how with increasing pressure, this line is changing from, that is increasing pressure means you are moving from P3 to P2, you are moving from P2 to P1. So when you are at low pressure, it is cutting here. When you are increasing the pressure, now this line is gradually shifting downward. And that is also logical. It is not that you just have to simply memorize. It is logical also, because just remember the Boyle's law. P and V inversely related. That means when pressure is very high, volume is low. So see, P3 is minimum pressure, right? So that is why the corresponding volume where it is cutting, that volume is also high. But P1 is max. So look at the corresponding volume. Just compare these three lines. You will be understanding that here Boyle's law also you can find how Boyle's law is maintained. So in this way, as that is questions related to graph is very common. So that is why you should have clear idea how these graphs we can draw. Fine. Which of the following graphs represent Charles' law correctly? So as it is relationship between V and T, and V and T directly proportional. That means when V will increase, T will also increase. And this type of two quantity, when they are present in x-axis and y-axis, and they are proportional to each other, obviously the nature of the curve will be like this. If it is inversely related, then the nature of the curve is like this. But in this case, as it is directly related, so when V is high, suppose this is low V1, this is V2. This is, if it is V1, the corresponding line I am drawing here, it is T1. Then it is V2, I am drawing the line, it is at T2. So see, when T1 is low, obviously T1 is low value than T2. So V1 is also lower than V2. And V2 is high, T2 is also high. So in this way, you can draw several points like this. So this nature of the graph is obviously cut. And if you just interchange it, then also it is correct. So this is true. This is also true. What about the third graph? In the third graph, we have taken V by T. But remember, as this from Charles' law, we know V is directly proportional to T. If you remove the proportionality sign, it is V equal to KT. Or V by T is equal to constant. So V by T, this ratio is always constant. Whether you draw it with V, whether you draw it with T, it is always constant. So that is why the value is fixed at this point. You are increasing the volume from here to here, you are increasing, but the value is not changing. That is the ratio of V by T is not changing. And that is true. So this is also correct. This is also. So all the graphs are basically representing the Charles' law correctly. Option B, correct option. So we have seen PV relationship, Boyle's law. In Charles' law, we have seen VT relationship. Now, another possibility, PT relationship. So obviously volume will be fixed, mass will also be fixed, right? So Joseph Gay-Lussac stated that at constant volume, so volume will have to be constant. The pressure of a fixed mass of a gas. So see, this is fixed, directly proportional to temperature. So here also it is directly proportional, just like the previous one. The Gay-Lussac's law is also sometimes called Amontone's law. So P is related to T in this way, directly proportional. If you remove the proportionality sign, you have to write it as P equal to KT or P by T equal to K. Now suppose we have taken two different states. One is pressure 1, that is initial. Suppose this is final P2, and P1 corresponding temperature is T1, P2 corresponding temperature is T2 respectively. Then from this law, what we can write? We can write P1 by T1 equal to P2 by T2. And that is true because of this relationship, that is P by T equal to K. In this way, if you take some more states, then it will be P3 by T3, P4 by T4 like this. So here if we see this graph, you can find similarity with the graph that we have in case of Charles law. The same. Only difference now in y-axis, instead of volume, we have taken pressure. And here we have total 4 lines. 4 lines at 4 different volume, because volume is fixed. So if we have changed the volume, obviously the line will be different. So 4 different volumes we have taken, and V4 is max, V1 is minimum. Here also you can see, as V1 is minimum, so the corresponding line, that is a blue line, that is maximum pressure, and this is max, but pressure is minimum, which is basically Boyle's law. Okay. Now here also the nature of the curve, that will be same. That is the same nature that we have observed in case of Charles law. Fine. So if we extrapolate it again, it will cut it somewhere here, and temperature is taken in degrees centigrade, but you can also consider it as 0 Kelvin. So if you shift the line towards this scale, suppose you are starting from here, then obviously the line will pass through 0, because now it is 0 Kelvin, not degree centigrade. When it is degree centigrade, there will be some intercept, otherwise not. So here we have taken 4 different volume, all are constant in each case, and this type of line is known as isochore. So remember the terms, when temperature fixed, the lines are called isotherms, then isobars, and in this case volume fixed, it is called isochores. We have a problem here. A rigid nitrogen tank stored inside a laboratory has a pressure of 30 atmosphere at 6 a.m. So it is a morning time when temperature is low, and when it is afternoon, then the temperature is increased 45 degrees centigrade. So you have to find the pressure in this tank. So basically here P1 is given, then T1 is given, P2 you do not know, T2 is also given, right? So very simple. T1 is 27, this is 45, P1 is 30 atmosphere, and this is, we do not know, that you have to find in atmosphere. But if you directly put in equation, it will be wrong, because degree centigrade we have to change it to Kelvin, then only we can get correct result. So here we have to apply this, that is PT relationship, the law that we have just learned, which is Gay-Lussac's law. And here nitrogen tank, it is mentioned that rigid nitrogen tank, that means obviously the volume is fixed. It means the volume is fixed, and number of moles of nitrogen, that is also fixed. So when number of moles fixed, volume fixed, that is mass and volume fixed, then only we can apply this relationship. Pressure is directly related to T. So that is why P1 by Q1 equal to P2 by T2. So here V constant, N constant, now R is constant, that is mentioned, but R right now you don't need. When we will learn ideal gas equation, then you will be seeing the use of it. So initially P1 is 30 atmosphere, temperature is 300. How you are getting it? Just with degree centigrade you have to add 273. Okay, so you can get 273 plus 27. So it will be 300 Kelvin, and 45 also you have to change. So you just have to add 273 with 45, and you will be getting 318 Kelvin. So just change the temperature to Kelvin, because this relationship is only applicable. That is when you are saying that P is directly related to proportional to T, that is applicable only when it is absolute scale. Remember the graph, when it is in degree centigrade, it is cutting here. So you cannot say it is directly related to it. There is some intercept. But when you have taken temperature in Kelvin, now it is going through origin. So that is why you can say that P is directly related to K only when temperature it is in Kelvin. Don't think it is in degree centigrade. This is wrong. So that is why you need to convert it from degree centigrade to Kelvin. Don't forget to do that. Okay. Now you can use this equation. So here only P2 is unknown. So from this equation you can get the value of P2. That is the nearest integer you have to take. So that is why 31.8 you have to write 32. The next law. Now it is volume and amount relationship. Now when it is amount, that is mass, we basically consider moles. You can also say number of molecules, but moles also you can say. Moles or molecules. So it states that equal volume of all gases under same condition. So suppose you have taken O2, N2, carbon dioxide, ozone, whatever gas you take. But suppose all are having equal volume. So volume is fixed. And other conditions are also fixed. That is temperature, pressure, etc. So when you can maintain this, then you can say that all these gases, that is their volume are equal, so they will all have same number of molecules. Okay. Now in other words, for an ideal gas, the volume is directly proportional to its amounts, or you can say moles, provided temperature, pressure, these two are fixed. Because if you are not fixing it, there will be that is, you cannot have this relationship. We know that all these different factors, that is properties, volume, temperature, pressure, amount, four things are basically there: temperature, volume, pressure, and amount of gas. That may be in terms of moles or molecules. So these four things are there. So when there are four things and you are trying to find relationship between any two, obviously the other two you have to fix. So that is why, as here we are checking the relationship between volume and amount, so you have to keep temperature and pressure fixed. Okay. So N we have considered as if it is number of moles. So V is directly proportional to number of moles. So when it is true that here it is written molecules, but suppose if I am saying that there is X number of molecules, and if you are dividing it by Avogadro number, because in one Avogadro, when we say Avogadro number, it is basically 6.022 10 to the power 23 number of any species. Okay. So when you are dividing this number of molecules X with Avogadro number, you can get N. That means X directly proportional to, that is equal volume, means equal number of molecules. You can also say equal number of moles, because X and N, these two are directly related, because Na is the conversion factor. When you divide it by Na, then only you get moles. So because of this constant, X and N, they are basically, they will change with volume in a similar fashion. So V is proportional to N, so V by N will be some constant. And if you consider any two state, initial state 1, final state 2, then V1 by V2 equal to N1 by N2, or V1 by N1 equal to V2 by N2. So V is volume, N is number of moles, the volume and number of moles of a gas, and this is also different set of values, obviously for other state. But remember, temperature, pressure, these two are fixed. Then only you can have this relationship. So now if we take in y-axis volume and amount of substance, you can write in. Then the nature of the graph, because it is simply y equal to mx type of equation. There is no intercept. V is proportional to n means what? V is equal to kn. So V is y, k is slope positive, and n is number of moles, which is in x-axis. So in this way you can compare it. And remember this Avogadro number, because if you want to convert molecules to moles or moles to molecules, the specific number of molecules that is present in 1 mole of any substance, not necessarily gas molecules. You can say 1 mole electron, 1 mole proton, anything. So specified number of molecules that is present 1 mole of any species substance, it is this number. But just remember, up to this 6.022 into 10 to the power 23, this is enough. So this quantity is called Avogadro number or constant, which you will require when you will change from number of molecules or number of atoms to number of moles. So when it is 1 mole, this quantity is present. When 2 mole, then this quantity into 2 is present, like this. So we have finished Charles' law, which is temperature volume relationship. We have seen the graphical representation. After that, Gay-Lussac's law, which is pressure temperature relationship. And this is third one of today's class, which is Avogadro law. So total 4 laws we have seen. Boyle's law, which is relationship between V and P. Then Charles' law, which is relationship between V and T. Then we have seen Gay-Lussac's law, which is relationship between P and T. And this is amount and volume, that means V and N. So these 4 laws we have seen. Now combining these laws, how we can get ideal gas law, because all these laws are obeyed by ideal gases only, though it doesn't exist, but it is only applicable for ideal gas. So if we combine all these laws, basically we will not combine all these 4, just we will take these 3 is enough, because when you will take these 3 V, P, V, T, already 4 quantities are covered. So even if you do not consider, it doesn't matter. So here we have taken Boyle's law, Charles' law, Avogadro's law, V, P relationship, V, T relationship, V, N relationship. So now you can get a relationship where all these quantities will be present simultaneously. So a gas that would obey Boyle's law, Charles' law, Avogadro's law under all the conditions of temperature and pressure. Basically, if you are thinking why we have not got Gay-Lussac, that will also be obeyed, because when some gas is obeying these 3, obviously the 4th one will also be obeyed. Fine. So here a gas that would obey all these laws under all the conditions of temperature and pressure, then it will be called ideal gas. And the equation that we are going to get by combining these laws, that is known as ideal gas law. Okay. So though it is true that such ideal gas doesn't exist in reality, it is hypothetical, and it is assumed that intermolecular forces are not present between the molecules of an ideal gas. Though that is not true, it is just assumption. So when you make this assumption, that is intermolecular forces are not present. Remember intermolecular forces in the first class we have seen, right? So when these forces are 0, then only ideal gas can exist. But that is actually assumption. It is not possible that intermolecular forces will be completely 0. No, that is not possible. So it will always remain, whether it is present very high intermolecular forces or low, whatever it is, but it will never be 0. Okay, so that is why ideal gas they do not exist. But if we consider this assumption, then only it can exist. So from Boyle's law we have seen this relationship, from Charles' law and from Avogadro's law. So now when you are combining all these 3, you will be getting V is proportional to N into T divided by P, because P is in denominator. So to remove this proportionality, we can have a constant, and this constant is basically R, which is known as universal gas constant. So V is proportional to NT by P. So just multiply all these 3 quantities, 1 by P, then into T into N. Remove this proportionality sign, you have to place some constant, and this constant is having a specific value for different unit. There will be different values of R. Fine. So this is proportionality constant, also known as universal gas constant. Real gases follow these laws only under certain specific conditions. So for ideal gas, what we have seen, remember the first line, what is mentioned, under all condition of temperature pressure. But when it is real gas, now you cannot say under all condition of temperature pressure it will be followed. Now there are some restrictions. Only under certain specific conditions. Which conditions? Those conditions where these intermolecular forces are practically negligible, though we cannot say it is zero. So that is, it is mentioned practically negligible. So there may be some condition where these interactions are very negligible. So real gases will behave, that is, they will be having a tendency to behave like ideal gas, but it is just close to the behavior of ideal gas, not exact. So ideal gas equation is a relationship between four variables. We have V, N, T, P, four variables, and it is the general law for any gas. So it describes the state of any gas, whatever gas you take. It is not specific for any specific gas. It is generic. So that is the reason it is also called equation of state or ideal gas. Okay. Now this universal gas constant, we will see how its values at different unit. So here you have to remember these values. If it is given in the question, it is fine, but if it is not given, in that case you will need these values. So when it is SI unit, per mole per Kelvin, you will always get it, whether it is SI unit or other unit. So in joule, the value is 8.314 joule per mole per Kelvin. Then if it is in liter atmosphere, instead of joule, now we have liter atmosphere, that is volume and pressure. But per Kelvin per mole, that is still present. Or you can have the value in calorie. Instead of joule, now we have calorie. Fine. So the value is 2 calorie per Kelvin per mole. So this part is common, only joule is changing to liter atmosphere or calorie. So if you are using the value of R, suppose you are using 0.0821. So remember, in that case, the volume must be in liter. Otherwise, it will be wrong. Okay. So these things you have to keep it in mind. Now, one by one, we will see how we are getting it. So for conditions where pressure is 1 atmosphere, volume is 22.414 dm cube, or you can say liter, dm cube liter, same thing. Okay. N is 1 mole and T is this value, 273. Now under this condition, we have seen the equation PV. What we have seen, V equal to nRT by P. Now V equal to nRT by P means R should be equal to PV by NT. R should be equal to PV by N into T. If you want to get the value of R in this unit, what you will do, for condition when pressure is 1, so this is pressure, this is volume in dm cube or liter, this is N 1 mole, and this is temperature. So if you put all these values, you will see the value you are getting 0.082, which is this one. Then dm cube ATM or liter ATM, whatever you write, per mole per Kelvin. So this is for one condition. Next condition possibility is under standard condition of temperature pressure, which is also known as STP. Sometimes you will also see another term, though not very common, STFE. So when it is STFE mentioned, in that case, the difference with STP is that now the value is not 273. Now the value is 298 Kelvin. That is the only difference with STFE and STP. So STP and STFE both are basically same. Only difference is here temperature is 0 degrees centigrade or 273 Kelvin. In this case, it is 25 degrees centigrade. That is ambient temperature. So A is for ambient, STFE. So here we have considered STP. So pressure is 1 bar. Though 1 bar and 1 atm, they are very close, but still there is some slight difference. And 1 bar is equal to 10 to the power 5 Pascal also. So these are different units of pressure, atm, bar, Pascal. Then volume is taken in meter cube unit, because now you are getting the value of R in joule. So SI, you cannot take dm cube or liter, you have to take it meter cube. So this is the volume, meter cube. N is again 1, T is just like before. So when you are putting all this is pressure, this is volume. So you see, this is dm cube, 22.4 almost, and this is 22.7, almost same. So for dm cube you are converting to meter cube, obviously 10 to the power minus 3 you have to multiply, right? Because you are from lower unit you are moving to higher unit, dm cube to meter cube, because 1 dm is 10 to the power minus 1 meter. So when it is dm cube, it will be 10 to the power minus 3 meter. So this is V, this is N, this is T, you are getting this. This is the second unit, second R value. Another possibility, slight difference. See, at STP conditions, which is used earlier, this STP that you are seeing here, this is basically recent what we follow. But earlier, this value is, there is slight difference. Earlier it was considered 1 atm, which is not 10 to the power 5 Pascal, which is 101325. Though 10 to the power 5 means what? 5 zeros, 6 digit. So here also it is 6 digit, but it is not exactly same. So you can say it is slightly higher than the previous one. Previously it is 10 to the 5. Now it is 101325. Okay, so obviously it is greater. This is the only difference with earlier concept of STP. So then it was 101325 PA, which is 1 atm. V is 22.4, just like this one, and temperature is, sorry, just 2 times. So in this case, the value of R that you will get 8.312, but you don't have to remember it. Just for information, I have presented it here. Otherwise, you have to use these values, not 8.31. This is the older concept that you don't have to remember. So this you have to follow, these two main. And sometimes calorie will also be used. So though there are older, that is we follow this, but IUPAC since 1982 defined standard reference conditions as 0 degree centigrade or 273.15 Kelvin. This value of pressure which is mentioned here, in contrast to its old standard of 0 degree centigrade and this pressure. Okay, so don't follow this, you have to follow this one. So this is all about R value. What problem we have here? At 300 Kelvin, you have a sample of 3 gram of any gas A. It is occupying the same volume as 0.2 gram of hydrogen, which is at 200 Kelvin. So gas A is present at 300 Kelvin, but hydrogen is present at 200 Kelvin. But volume of both are same. Pressure is also same. So from this information, you have to find the molar mass of gas. Now it is asking molar mass. So if you can find the that is number of moles, from this also you can find the molar mass, because given mass is 3 gram and we know that given mass divided by molar mass, that is actually number of moles. So if you can somehow find number of moles from PV equal to nRT ideal gas equation, given gas mass is also known, you can easily calculate molar mass. So your aim will be to find out number of moles from the equation PV equal to nRT, because that is applicable for hydrogen as well as the gas given A. So for gas A, first you can write for gas A, pressure is P, because we do not know what is the pressure. Temperature given 300, volume also we do not know, mass we know 3 gram, and molar mass suppose it is capital N. So when you will use the equation PV equal to nRT, in place of small n you can write 3 by capital N, isn't it? So this will be the equation PV equal to nRT. PV we have simply written PV in place of n. Now you can write given mass by molar mass, R universal gas constant and 300. Now keep it like this and come to another gas which is hydrogen. Now for hydrogen, here pressure is also same, because that is mentioned in the question. Same pressure. Volume is also same, because that is also mentioned. Temperature different. Mass is also different. Given mass is 0.2. And we also know the molar mass of hydrogen. Basically, it is simple, we know it, but still it is given in the question. So here also you can use the same equation PV equal to nRT, and in place of n, now you can write 0.2 by 2. In place of temperature, you will write 200. So this is the equation, just like previous one. So suppose this is equation number 2, this is equation number 1. So 1 is basically equal to 2, isn't it? So that is why, after all, what you are getting? This part is for gas A, this part is for gas hydrogen. So these two are equal, cancel, and only m is unknown. So you will be getting the value of m, that is molar mass, like this. Okay. So here in this problem we have learned how we can use the equation, that is ideal gas law, PV equal to nRT. So as it is general gas law, you can apply it for any gas A, and you can also apply it any gas, that is other gas mentioned, hydrogen. And as the left hand side quantity is same, we can write these two quantities, they are equal to each other, and the unknown value, that is the molar mass of A, we can obtain. Sodium chlorate NaClO3 is used in spacecraft, and the purpose is to produce O2. And how O2 is produced, that is also mentioned in this question, that is already given. Now daily consumption of pure oxygen by a person is 492 liter at temperature 1 atmosphere, Kelvin scale 300 Kelvin. From this information, we have to find how much amount of sodium chlorate in gram unit is required to produce oxygen for the daily consumption of a person at this condition. So daily consumption, the volume is required 492 liter. Okay. Now as this equation is given, from this equation, what info you can see, what info you can get? This is balanced equation, right? You can check it, it is balanced equation. So when it is 1 mole of sodium chlorate, you are getting in the product side 1 mole of oxygen. Now you know what is the amount required, that is how many moles of oxygen is required by that person daily, that we know, that is mentioned, and this amount is 492 liter. Temperature given, pressure given, so this is volume, this is pressure, this is temperature. If you use the equation PV equal to nRT, n value you can obtain, because T, P, V all are known, R is also known, it is constant, we know the value. Only n is unknown, so n for oxygen you can find. Once you know the n for oxygen, it is same n for NaClO3 also, because both are same mole ratio, isn't it? And once you know the number of moles of sodium chlorate, you can also find the amount of NaClO3. How? NaClO3, as the formula is given, you can calculate molar mass. So if you know molar mass, if you know number of moles, obviously you can get the amount required in terms of gram. So first we will find molar mass of this compound from which O2 is generated. 23 for sodium, then 35.5 for chlorine, and 3 into 16, that is for oxygen. So this is 106.5 gram. So just keep it aside. Next you have to use the equation PV equal to nRT, from which you can get number of moles of oxygen. So moles of oxygen is equal to, that is PV equal to nRT. So N is equal to PV by RT. Okay. So this is PV by RT. P is 1 atmosphere. 492 is volume in liter. So as it is in liter and atmosphere unit, P and V. So you have to use R value, which is also given like this. R is T is 300. So this is 20 mole. And this we already know. 1:1, which is clear from this equation. And you also know the molar mass. So mass of NaClO3 will be, basically you are calculating the given mass, which is equal to molar mass, moles into molar mass. So you know moles, you know molar mass. So ultimately it will be 2130. Okay. So we are at the end of the session. We will end here. Thank you for listening.